I'm going to show you how to interpret binary, how to count in binary, and in the last tutorial I showed you exactly what specifically binary is. Now I'm going to show you how it is used. Okay? So, let's go. Now, let me open up some type of text file. Binary.txt. Okay. Basically, binary, as we already know, okay, uses two different symbols and characters to explain something. Okay? Like I said, 0, 1, two different characters, and you could say 2 and 9, two different characters. If we both agreed on it and sent out a string and said that this means that, that's what we can do. Okay? Okay. So, how to do things in binary. People say that our computers read zeros and ones. Okay? Now, I might be going on a limb in saying this. I don't know if that's very true or not. Okay? And I'm going to tell you why. I do know that zeros and ones is a base 2. Okay? But I don't understand why a computer would need to read a 0 or a 1. Okay? A computer, being an electrical device, would not need to read 0 and 1 as a 0 or 1. What the computer, I think, interprets is a 0 and 1 to be possibly, okay, this changes with different computers in time, like in the 30s and now. This is a little different. But say if we had a light switch, okay, and we did not turn it on, the light switch was off, okay, and we flicked the switch, that would then turn on the light switch. So there's no juice or no power going to the light switch, or no power going to the light now until we hit 1, and then we open up the circuit and let that light come on. It's electrified now. Okay? So if we say 0 to be no volts, okay, and then when we connect, or then when we turn on the switch, we will say a 1 to be a positive, we'll say a positive volt. Okay? That's a change. That's a change in time. Okay? A change in time will indicate something. If you were across the street and I told you to look at my porch and I'm going to flick the light on twice, that would mean something if I told you what it meant. Okay? That's a way to communicate to each other. Okay? So, basically, like I said, our computers are just a big bunch of electrons moving around. And our computers read voltages, magnetism, what's magnetized, voltages, negative voltages, flat voltages, stuff like that. Okay, I don't know about flat voltages or nothing ever. Okay, I'm pretty sure it's positive 5, okay, and negative 5. But for the 0 and 1 binary thing, I'm going to stick with 0 as being nothing, okay, and 1 as being on, okay. All I'm doing is on and off, okay. And you can array this in a different form if you're familiar with Morse code. That equals an A, okay. And if I throw these together, if I have two quick beeps and a long beep, that is something else, okay. That is something else, but this is space 2. Okay. Uses two different type of symbols, one being a long beep and one being a short beep. Okay. Two variants, and then that's agreed on, and that's what Morse code is. Okay, so that's another example. But as far as voltages go, your computer reads voltages. Whatever's stored on your hard drive is magnetized, okay? And data is held by the magnetism it has, right? In order for you to magnetize stuff, it can have voltage applied to it so that it would retain that type of magnetism. It would either be a positive magnetism or it'd be a negative magnetism, okay? Maybe north to south. I don't know if that's right. Is that right? I don't know. Right? But there is a magnetism. That's the way that our hard drives hold data. That's the way CDs hold data. Everything gets magnetized and it holds data that way. Okay? If you were to clear the magnetism out, what happened here? Number lock is on. Okay. If you were to clear the magnetism out and restore it to 0, well, there's no data. Okay? And if you were to then positively charge that area of data, alright, then that would represent a 1. Okay? So that's that. As far as our computer's reading in binary, zeros and ones, everybody says it does, and I have no reason why to say it doesn't. But I would like to just think a little deeper into this, and actually what is going on. And I would like to bypass the 0 and 1 thing as being that's exactly what our computers read. Maybe it does. I'm not sure. I'm not that smart. I accept it. I'm not fighting it. But I do tell you that there is voltages in the machine. And zeros and ones on a binary system can represent a positive volt and a negative volt. Okay? So, with that in mind, let's work on some binary. Why is it important to know binary? It's not. Alright? We don't type in binary. This is not proficient, efficient for us to use to enter into a computer at all. Okay? This does not work. We need to use a hexadecimal to enter that stuff into a computer. Okay? And since we use a hexadecimal, it gets interpreted so we can read it back through ASCII. Okay? We can read it back in hex too. We can read it back in hex. It's just a little more convenient in ASCII. Okay? So that's that. And on to binary. This here means nothing. This string can go on for infinity. It means nothing. Nothing at all. That's just space and time. Nothing. When you throw a 1 into it, that's a change, and that means something. So somewhere in time, that means something. Okay? What it means? If I was a big YouTuber, I'd be like, decipher this, and I'd send you a candy bar or something. It's not important that you decipher it. Okay? But that would be cool to know what it is. But 1 indicates a rise or plus volt. Okay? 2 or 0 is no volt. Now 0 may not be no volt really, but for the examples of this tutorial I'm going to say no volt because it's easier to understand that way. Okay? And the way that things in binary are read, okay, this is a string of stuff. Okay, the way that things are read in binary, there's something called an order. Okay, if I say this is a test. Okay, we can all say that we know that this says this is a test. Okay, now if I type this backwards, okay to type them backwards. If we type this backwards, the string, or what we just said, what we agree on, that this is a test. These words say this is a test. We agree on this. When you type this backwards, whoa, I screwed that up. ST? Yeah, SE. When you type this backwards, this doesn't mean the same thing. D set C A sit. Alright? Forwards is one way, backwards is another way. We understand that this is a test, that these words here, or these characters here form. This is a test because of we are under an assumed standard that we will read from left to right. Okay? That's how we read. That's a standard established for us, and that's how you read everything. If we were backwards or totally insane, alright, this is how we would read from right to left. Right to left. Okay? But we don't read right to left, okay? We read left to right. As human beings, that's what we do. Now this can also be known as, in the architecture sense, this can also be known as something called ediness. I didn't spell that right. It's pronounced ediness. Alright? Ness. Okay? That's not how it's spelled. In either case, but it's pronounced ediness. Okay? And what that is eddying. Okay? There's two types of eddying. There's little and big eddying. Okay? And they are just two different reading orders. Two different ways to read data. Two different ways that our computers read data. Okay? Two different ways that our processors read, store, and everything else about data. Ediness there's a ton on it and why it's important, why there's a difference, why there's a change, and it has to deal with algorithms and all this other crap like that. Alright? But for this basic instance, I'm just going to say that it is an order, a way to read. Okay? It is a way to read so that we can keep it uniform, so we can understand it, or set a standard, or attach to the standard that's set already. Okay? Little endian. Okay? The order is least significant byte. Okay? You read from the least significant byte. Okay? Or right to left. Okay? So now, let's pause there. Let's say little endian is from the least significant byte, or it's right to left. So, if we were using little endian, okay, we would read from this position back this way. Okay? The greater number is to the left. Okay? Here. That is the greater number. Okay? Okay. Now, that's with little endian. Now, there is a big endian. Okay? There is another reading order type. And if you want to think about it this way, us as human beings, okay, when we go ahead and we type out 1, 2, 3, 4, 5, 6, 7, no, let me not do that. Let me say this, da ba ba. This is how, the way that we read numbers is 13,323. We read them from left to right, okay? Or, us humans use big endian, okay? And you would read the number over here, okay? Now if we used little endian and we read it backwards, 32,331 is a bigger number. It's a different number, okay? It's a different way to string and array the characters. Now, why is ediness important? Because if you're going to read code, if you're going to look at machine code, or if you're going to look at things at such a low level, you need to know which way to read these things. Okay? And I'll give you a perfect example now. Hex dump C this dot show. Okay? And basically, the way that things are being read here, okay, they come out. I'm gonna pick a better thing. They come out, in the computer it reads it backwards than what we put out. Okay? And an example here, 6E equals N. Okay? Yes, we do read stuff from right to left over here. That's because we're human beings. And can you flip that around backwards and expect to read it? I don't think so. Okay? But our computers interpret it that way. Okay? What happens is this stuff comes out and is different. Alright? It gets flipped around. Alright? It's enough on that. But this is Eddiness, and it's our reading order. Okay? Now, Intel, my processor, actually it's an AMD, but it's compatible with Intel. The x86, alright, uses little endian. Okay? Which means that in binary form, I need to, when I represent binary form, I'm going to read from right to left. Little endian means that least significant bit first, or you read from the least significant bit first. Okay? It's backwards. Okay? That's how you interpret binary, depending on your architecture. Okay? And binary, see, since Intel is God and everywhere, few things use big endian, or not as many things use. Things do use big endian. ARM processors do use big endian way of reading. Okay, they do read from the left, or at a machine level. I don't know if it interprets that way. I don't think it would be interpreted that way, because if it did, then binary would really be screwed up for people with those processors. Alright? But I think maybe it goes to an interpreter so that we could read them backwards, and what we type in maybe gets flipped around to the computer so that it still uses its correct Eddiness. But for us reading, our reading purposes, that is how we should read. Now with that in mind, we're going to say something here. Say 17.45 or 43. Okay? This works the same way that our computer, how we can read and interpret binary. Binary is not that hard at all. If you notice here, this is 17, right? 7 is in the ones place, I think. Okay? The dot signifies a different transition in space, right? 4 is in the what? Tens place. 3 is in the hundreds place. Okay? Now if we were to continue this on, okay, then we would say that this here, this 0, this first 0 after 4-3 is in the hundreds, thousands place, 10,000s place, 100,000s, millions, 10 millions, 100 millions, yeah, 100 millions place, okay? And then if we throw a 1 in there in the billions place, yes, we have to talk about it. You understand? Or if we throw a 5 in there, we have to talk about it, okay? So it would be something 5 billionths, okay, with a TH, okay? So basically, we know that these places indicate different levels of powers, actually, okay? Different levels of elevation of powers. These numbers are, that's what those numbers do. And also too, I want you to remember that we can throw a whole string of zeros ahead of this, and this means nothing at all, okay? This 17 exists, okay? You can infinity back out that way, alright? means nothing. There's no change. That means something big. Okay? So basically, binary is interpreted the same way. And how it is interpreted, get these zeros off the screen for you guys. How it is interpreted is there are signified places of stuff. Okay? And usually, each one of these symbols in here, we're not going to call them numbers, we're going to call them symbols. Each one of these symbols are relevant to us as numbers, which are zeros and ones. Okay, we use zeros and ones because that's what we do, but those are still symbols in a basic form. This collection of binary numbers, symbols, or a collection of binary voltages, this collection of on and off, on and off, on, off, on, off, on, off, Jesus, on, off, 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 and the signal, whatever. Okay? This collection of stuff has places. Okay? This collection of stuff is also called a collection of bits. It's one bit of information. Everything here, this 1 is a bit, 0 is a bit, 0 is a bit, 1 is a bit. Anything in this string here is called a bit. They're alternating bits. Two types of bits. On and off, plus and negative, 1 and a 0. Two types of bits. Okay? Okay. Now, let's bust these bits up so we can actually read what they are telling us. Okay? Let's bust these bits up, and we're going to count over 1, 2, 3, 4. That's a 4-bit slice. Okay? We are separating 4 bits, and let's do it again. Let's say 1, 2, 3, 4. Another 4-bit slice. 1, 2, 3, 4. Another 4-bit slice. 2, 3, 4. That's another 4-bit slice. Okay? This here is a 2-bit slice. Alright? Let's add that to it to make it another 4-bit slice. Okay? These 4-bit slices, each one of these 4-bit segments, we can say is a 4-bit byte. Okay? 4-bit byte. Okay? It takes 4 of these bits. To create 1 byte of information. Okay? Let's say 4-bit equals 1 byte. Okay? So it takes, like I said, it takes 4 of these bits to create 1 byte of information. This area is 1 byte. This area is another separate byte. Okay? And it contains 4 bits of information. It contains 4 individual bits of information. Same thing over here. This is a 4-bit byte. Okay? Now they actually did use 4-bit bytes back in the day. They also used 6-bit bytes back in the day. IBM, I want to say before the System 360, which is like archaic, ancient, and probably as big as my living room and your living room and your neighbor's living room all combined. Okay. They were having a problem. They weren't having a problem, but to create a standard, IBM was using the 6-bit byte. Or one of their bytes was 6 bits long. Okay? Is that right? That is not right. One of their bytes was actually 6 bits long. Okay? Well, that was good for IBM, but when IBM had to contact other computers that were or other companies or other computers that were made by other companies, and they were on a 4-bit or say an 8-bit byte type of format, well, there was a problem. Why was there a problem? Well, because there's a 12. You know, 6 double is 12, 8 double is 16. Okay, so that right there is a loss and transfer. Now they do meet up. They do meet up, say, at 24. Okay, they do meet up at 24, but if you think about it, the difference between 6 and 8, you would lose data from, see, you would lose the 12th bit, or the 12th, you would lose a chunk of data. You would only pick up the data at 24, where 24 is compatible with 8. Okay? You would pick up that chunk. So basically what would happen is, let's say Quasimodo. Okay? Each one of these is a byte. I skipped ahead, but I can pick it up right here. Each one of these is a byte of information. Okay? And with the 6-bit byte and the difference between the 8-bit byte, since they meet up at 24, 8 double is 16, but 6 double is 12, you skip something, you lose something. So maybe you lose that, okay? And maybe you lose this, okay? And maybe you lose this, okay? So when I send you Quasimodo, what you get on the other side of the world is Kuzoi. Alright? Literally, that's not what happens. But I'm trying to show an example between the incompatibility of one company having a 6-bit byte while the other companies have a 8-bit byte or a 4-bit byte. Okay? And what happens is communication will break down. So IBM improved their standard, and they switched from the 6-bit byte to the 8-bit byte. Okay? And the 8-bit byte became more recognized as a standard way of computing and storing information and sharing information, so they would stick to 8-bit bytes. Okay. So, like I said, delete this. Like I said, that this here is a 4-bit byte. Okay? Now, if I want to share information, this here now is an 8-bit byte. You will see that there's 8 bits, 8 individual bits here, constituting 1 byte. And that's the way that the world works now. Okay? They roll on an 8-bit byte, or they roll on an 8-bit equivalent byte. Okay? Now, let's switch these back to 8-bit bytes and add 1, 2, 3, 4. Okay, these are all 8-bit bytes now. Now, certain processors do certain things. There was an 8-bit processor. There was actually a 2-bit wide processor that you could use. I think Fairchild had it. Okay, the Intel 4004, I believe, was, man, I think it was 4-bit byte. Okay, it used a 4-bit byte, and the 8008 was an 8-bit processor. Was the first 8-bit processor. Okay, so basically it took 8 bits and made it a byte. Now, when I say bits and bytes, if I say America, okay, it takes 8 bits in 8-bit processing. It takes 8 bits to signify an A. Okay? It takes 8 bits to signify an M, E, R, I, blah blah blah. Okay? Each one of these contains 8 bits. Okay? Alright? That 8 bits constitutes one of this, here where this tick is, This is 1 byte of information. The letter A is made up of 8 bits, and it constitutes 1 byte. 1 byte of data. Okay? On an 8-bit processor. Alright? Now, that's with the 8-bit processor. How about a 32-bit processor? I'm using an Intel x86, which is a 32-bit processor. Some of you may be even using an Intel x64, right? It takes 64. Intel 64-bit takes 64 bits. 64. Let's get rid of this. Takes 64 bits of information. Okay? However many this is, it takes 64 bits of information to create 1 byte, or it takes that much to create 1 character. Okay? So that's what happens, and there's advantages to 64 bits. Pretty much, you can move data at a crazy rate. With the 8-bit processor, you can move data, but your processor reads bits at a time, bytes at a time. Alright? If you have more stuff contained in a byte, you can read more at a time. Faster graphics processing, gaming, whatever. Okay? Data transfer, whatever. Alright? So that's what happens with a 64-bit processor. It has 64 bits, 64 characters in it, constituting still 1 byte of information. Okay? Now, I'm going to stick to 32 bits. Okay? I'm going to stick to a 32-bit architecture. And it takes 32 bits to make an A. It takes 32 ons and offs to make 1A. Okay? 32 ons and offs to create 1M. Okay? Or 1 byte. 32 ons and offs to create a byte, which is E. Okay? That's how it goes. And these numbers are divisible by 8. Alright? 64, 32, 256 is divisible by 8. All the way down to 8, 16. Alright, and you get 16-bit processors, which was the Intel X80, or the Intel 8080s, no, not 8086, but the Intel 86 processor. Okay? Not 8086. Can you say? Yeah, it was 8086. I'm sorry. Intel 8086. I might be wrong. The 386 was a 32-bit processor. That's for certain. 8086, I think, was a 16-bit processor. Okay? Commodores, they used 16 bits. Okay? To constitute 1 byte. Okay? That is bits and bytes. It's not that hard. It's not Martian, like people like you have to believe. It's not Martian at all. Okay? So we constitute 8-bit bytes. We're going to stick with the 8-bit byte here. And put this up here so everybody can read it. 8 bits equals 1 byte. 8 ticks, 8 ons and offs creates 1 byte. Okay? Now, to stay true to form here, this is only a 24-bit wide representation. Alright? Or, if you want to do some math, 24 divided by 3, or 24 divided by 8 is only 3 bytes wide. Okay? Let's amp it up. 1, 2, 3, 4, 5, 6, 7, 8. That is a 32-bit wide string. Okay? 32 bits wide string. Okay? Or it's 4 bytes. 32 bytes. No, 4 bytes. be, but doesn't matter. That's that. So when you have a 32-bit processor or whatever, it throws all this stuff together. Okay, throws all this whole string of stuff together here. Okay, positioning, all this stuff, where it's got to go in the processor, what type of thing is it? Is it adding and subtracting, whatever like that? All that stuff means something, and it constitutes what? One character, one char. Char, I don't mean only as a character as A, B, C, or D. I mean 1, 2, 3 spacebar, freaking pipe symbol, whatever like that. Okay, it indicates that you're throwing all this stuff through the processor at one time on a 32-bit processor. Now, like I said, you can imagine on a 64-bit processor. Alright, if this is 32, 64 is double this. Alright, you're throwing all that stuff at the processor at one time. The advantages are very, very incredible. Okay, more data can go through the wire at any time. Alright, now, you programming guys know what I'm talking about when I say something and I say octet. Octet. Now, octet is not really used too much in an architectural type of sense, okay? But octet, if you break it down, octet meaning 8 tet, or a clump of 8. Okay? It takes a clump of 8, 1, 2, 3, 4, 5, 6, 7, 8. Takes a clump of 8 bits and separates them. Alright? This dash symbol would just be an octet, or a chunk slice, or a byte. Okay? Are octets bytes? Are they bytes? Can we say they are bytes? Yes, we can say they're bytes. In a networking sense, but we're deeper than that right now. And octet for this will not be a byte of information, but will be a slice of 8 bits of information if I say octet. Okay? Okay. Super deduper. Now, basically what happens is, back to how we read stuff, and again, let me throw up my little thing here. Let's say 17.099. Okay? How we read stuff from left to right, because we're human beings. Okay? After the decimal point, okay, we have a tens place, we have a hundredths place, and we have a thousandths place. Okay? And you know, the rest of them, they all continue on. Now with this computer, with computers, we're going to read from the right to left, or backwards. Okay? And with computers, they read like this. When you want to read binary, I have a feeling I just screwed up with my tab key. When you want to read binary, okay, in this position here, from left or from right to left, this is a 1. Okay? 1 double is 2. Okay? 2 double is 4. 4 double is 8. What do you say? 8 double is 16. And we'll stop there for right now. Okay? Let me shore them all up. Okay? So basically, what I want to say is, whatever is in this first position, whatever, if you're on little endian, and this is the way that you read, little endian is least significant byte first, or from right to left. If there is something there other than no volts, we're going to talk about volts now. If there is a plus volt, not a minus volt, okay, or a no volt, and ones indicate a positive voltage or a turning on, or when you flick the light. If there's something there in this place or in the ones place, it is considered to be 1 active. Okay? Okay. Now, if you notice here, there is nothing on here, or there are no volts here. There is no data there. And that's in the 2's place. That 2 is not active. Okay? Same thing with the 4's place. In the 4's place, there is no voltage. There is no activity. So a 4 is not counted. Okay? Now, in the 8's place, there is activity, there is voltage. So it's counted as on. Okay? So what you would do is you would take your other on voltage. Okay? You would take whatever's already on. 1 is on. And also 8 is on. Okay? And if we stopped, we could say that equals 9. Okay? But we're not going to stop yet. 1 is on. Okay? Or 8 is on and 1 is on. Okay? Our sum so far is 9. Alright. Now, this is where GIMP should have come in to good play. But because I am an idiot, I don't like to use that stuff. Let me see if I can do a handy dandy crossover. Man, that worked out perfect, didn't it? Okay. That worked out fine. Super. Look how good that worked out. Alright. So, like I said, we have a 1 in... we have voltage in the 1's place, signifying a 1. Voltage in the 8's place, signifying that there's 8 on. Okay? Then we have no voltage in the 16's place, so a 16 is not a number we need to add into our pile. Okay? Now next, we would have a 32. 32. I knew this would break down sooner or later. Lord Jesus. Okay. We would have a 1 would be on. Let's go diagonal on this, right? A 1 would be on in the 32 section. Okay? So whatever number we already had, which was 9, we add 32 to that. So that is 41. Okay? Okay. And that's just how it goes. How it goes. Right? This here would stop because that's the end of our byte. Right? But if that was not the end of our byte, then this whole thing here, it would keep doubling. And we'll go all the way up to where it stops again. 2 8 bits is, what is that, 64. This is a whole 64. No. That's 8. That's 8. This is 16 bits wide. Okay? So 16, I don't know. And it's not important exactly what it is. But it is important that I show you the places and how it goes. But this would continue. This would be 64, and you got 128, alright, and then you got 256, and then you got 512. Okay, they would go all the way up. Okay, it would just continue. Whatever numbers you have originally, any numbers that you have originally, they would just keep doubling. Okay, all the way up even to freaking 200, whatever, that much. Okay, they would just keep doubling all the way up there. And if you had a ton of zeros, like 7 minutes worth of zeros, okay, and then you had a 1 in front of that, you would have to find out what that bit represented. Okay? Okay. If that bit represented 600 and trillion times 10 to the freaking 20,000 or 10 to the, yeah, that's what you would find. That number would have to be added. Okay? Or that voltage would have to be recognized. Okay? So, with that in mind, I'm going to say this 1, 2, 3, 4, 5, 6, 7, 8. We're going to split it off again into another octet. Okay? We're going to go back originally to where we were. And we're going to get rid of this 16 stuff, because you know that these double. right? Right? Okay. And then let's cut this again. Alright? We'll cut this again, and we'll do more on some how. Okay? We'll cut this again. These two here is let's now take it from an 8-bit byte. We're going to take it back down to a 4-bit byte. 1, 2, 3, 4. Okay? 1, 2, 3, 4. That's it. 1, 2, 3, 4. Take it down to a 4-bit byte again. Alright? That way I don't have to keep throwing off angles on you guys. Okay? Now, this here is a 4-bit byte. It takes 4 bits of information to create 1 byte. Okay? That 1 byte is 1 character. Okay? Or 1 number. We're only going to do numbers. Alright? Now, we're not going to represent characters as far as A goes. We're going to represent characters as far as numbers go. 1 through 10. No. 0 through 9. Okay? So, as you can see here, like I said before, there is a positive voltage or a 1. If you look at it in voltages, as far as positive and negative voltages go, you're going to have an easier time than looking at 1s and 0s. Okay? Look at it as a voltage, because it is a voltage. Rather it's positive, rather a 1 is a positive volt, or a 1 is actually a negative volt, as in at an Alsop-Berry computer, he actually ran at a high voltage all the time. So if he ran at a high voltage all the time, he would say 1 would be on. So pretty much his computer was on it all the time. The only time he ever lost voltage was when he created a deficit in voltage, or 0 or -5, or actually it wasn't a 5, it was more like a 150 volts or 115 volts. When he created a negative 115 volts, that would indicate a drop. What would indicate a position of 1. Okay? But he was running on highs and lows. Look at his computer history museum talking back in 1981 to John Adanasoff. And you'll see some of his source code, well, his assembly code. And it wasn't 1s and 0s. It wasn't 1s and 0s. It was highs and lows, highs and lows. That meant something. And I think he had it separated into 3-bit bytes. Okay? This is binary. This is binary right here. 2 different symbols are only used, and they're spread out in such a way. Okay? Highs and lows. So with Adanasoff's computer, his high voltage was the normal, or reversed. Well, maybe it's reversed, because if you think about it, does it create, I think it takes more energy to create a spike than to create a deficit, right or wrong? If you think about a constant flow of voltage, a light being on, or a constant level plane, in order for you to communicate things, is it easier for you to heap with H-E-A-P, is it easier for you to heap up a pile of rocks, or is it easier for you to punch a hole? And if you punch a hole, that would indicate something as far as a change. And if you indicate change, you can symbolize that change to mean something. Okay? And that's what he did. His computer ran at a high volt all the time, and it created a deficit. And when the deficit ticked across, that deficit was the change that either was a 1 or a 0. Alright? And like I said, you can signify those 1s and 0s with places that will mean something. Now, for instance, let's go back here. Let's say this here equals 9, right? Right. Why? Because the 1's place, there is voltage on. Okay? The 2's place, nothing is on, there is no voltage. No voltage in the 4's place, 8 is on, and the number 1, there's a voltage in the 8's place. This equals a 9. Okay? Now, let's do this. 1, 2, 3, 4. I just screwed that all Now, in this 4-bit byte, if we have a 4-bit byte computer, which I don't, you don't, if you did, you could not be watching this at all on a 4-bit wide byte computer. But we're only separated by these 4 bits here. And then we start again. We will say something like this. That is the 1's place. This is the 2's place. Okay, this. Jesus. This is the 3's place. This is the 4's place. No. Oh God, no. 1, 2, 4. That's the 8's place, okay? So now, if we have here in this first byte of information, bits and bytes, like I said, are, bytes don't change. It's the amount of bits in those bytes, okay? Bytes don't change. Bytes are slices. Bytes are heaps, okay? Bytes don't change. If in this first byte we have this voltage on, indicates this number 9. In the next byte we will have a 0 volt and 1 in the 1's place. In the 2's place we will have a positive volt in the 2's place, so we count the 2. In the 4's place there is no voltage, so we do not count 4. In the 8's place there is a voltage, so we count that number. Okay? So in this second byte of information we will have a 2 and we will have an 8. And for you fancy guys out there, what is 2 plus 8? Can anybody say what 2 plus 8 is? Anybody show me how to work Vim so I don't tab everywhere? We have a 10. In the second byte of information, there is a number 10 located there. Okay? Now, let me move this over. Yeah, let me move this over. Okay. And I'm going to move it over one more time. I think so. Yes. Yes, John Spartan, you're getting pretty smart here. This is only for 4-byte wide instruction. Yeah. 4-bit wide byte. Okay? So, we're going to skip over this dude right here, right? Why? Well, we can do some reasoning real quick and say that, 1010 equals 10. Super. Well, 1010 also equals 10. Super. So, you know what? Posterity. Also say that this byte here, this 4-bit wide byte, contains the number 10. Okay? In a decimal form. If it was a hexadecimal, let's do hexadecimal now. Let's see what that would look like. Okay? Let's do this. We'll say in the 1's place there is a positive volt. Okay? So we'll say 1. 2's place there's also a positive volt. So a 2 is also on. In the 4's place there is a positive volt, so that is also on. In the 8's place there is nothing, so that is not on. So what would this be here? Quiz yourself. This would be a, what is that? 6, 7. My God, I mean, I need to stop doing the tab, man. Stop tabbing. Okay? So this contains a 7 in this byte. In this 4-bit byte. This number 7 is contained therein. Okay? Using a base 10 principle. Okay? Now, we can switch it up. If you use a base 16 principle, what's the difference? There is no difference. Actually, there is a difference. Should I talk about it now? No. We're not going to use a hexadecimal format. We're only going to use the decimal format. Only up to 10, and after 10, it can't do anything else. Okay? If I use the hexadecimal format, I had to figure out what 10 is in hexadecimal, and that is not even a understandable character. It's not like A. It's not like a number 1. It's something else. Think about it. If it's below 20, when a number is below 20 in the hexadecimal form, it's other stuff. Okay? It's other commands, other kind of things like instructions and stuff like that. Right? Above 20, it starts with the space key. The number 30, numbers start at 30, so number 1 would be 31. Okay? So I'm not going to go into hexadecimal and try to convert this out. I don't need to show you how to read binary. Okay? Now this is something good to talk about. In the ones place, there is a positive volt. Positive volt signifies by 1. So there is voltage in the ones place. Okay? There's no voltage in the twos place. There is voltage at the fours place, and there is voltage at the eighths place. Okay? So what we have is the number 13. Okay? That's what's going on. Okay? And we're only using an 8-bit byte. That's why these numbers are stopping at 8 and repeating over here. 8 bits, or 4 bits, a 4-bit byte. Okay? Now, that's what that is. Take a second, look at this. If you don't understand it, rewind the video. If you don't understand it, why don't you take it off of YouTube with YouTube Downloader and watch it and have fun. Alright? That's what's going on here. Now, I'm going to strip this apart here and no longer use the 4-bit byte. Let's cut it out and make it an 8-bit byte. Okay? Okay. Okay? Shoki doki. That now is a 4-bit, that now is an 8-bit byte. Let me take this out too. Okay, you guys know exactly what's going on now. This here, let me take this one out. Make this a 4-bit or an 8-bit byte. Each one of these takes 8 bits. 8 bits of information to create 1 byte now. It's different than a 4-bit byte. Why? It's only because of the separation. It's only because of the bit to byte count. Okay? This is an 8-bit byte, so this would be in the ones place here. This is the twos place here. Okay? This is the... Let me just keep doing this here. That's a little easier. Right, Charlie? Sure thing, Dan. Yeah. Okay? I wonder if I can copy that. I know I can. This here is the ones place with a positive volt. This here is the twos place with a no volt. This here is the fours place with a no volt. This here is the eighths place with a positive volt. This here is the 16th place. See, the thing is now, remember what I said, that these numbers, these numbers double. And if you always remember that these numbers double, you'll never have any problems whatsoever. You start with 1. Alright? 1 times, well, 1 plus, how can I say this not in a number sense? 1 and 1 is 2. Okay? 2 and 2 is 4. 4 and 4 is 8. 8 and 8 is 16. 16 and 16 is 32. 32 and 32 is 64. 64 and 64 is 128. 128 and 128 is 256. 256 double is 512. 512 double is 1024. 1024 is 1 gigabyte. Isn't it funny how 1 gigabyte is actually not 1 even like we would think? It's 1024. The reason why is because of bytes. The reason why is because of the 8-bit byte. Okay? 8 is a multiple that we have to continue to carry on. That's why 1024 is not what we would think it to be of 1 gig plus 24 megabytes, or is not an even 1,000 megabytes. It's 1024. Okay, because of the 8-bit byte. 8-bit byte. Yes, I am right. Okay, so never forget that these numbers double. You'll never run into any problems whatsoever. Okay, now I'm going to skip this first octet and start with this. Okay, this here we will say is at the ones place. 2's place is on. 4's place is no volt. 8's place is a volt. This here would be the 16th place carries a volt. Okay? And remember that those just keep going up. There you go. That's so pretty. Okay, these just keep rising. Okay, within this relative frame of an 8-bit byte area. Okay, 1's place, 2's place, 4's place, 8's place, 16's place. This is on, so this number does contain the number 16, or does contain a 16. Okay, 32. 32 is on, so you have to count 32 in your number arrangement. 16 plus 32 plus 2 plus 8. Okay? 64 is on. You must count 64 in your number arrangement. 128 is off. You don't have to count that. Okay? Now you want to be funny? I guess. Let's count them out. Sure, why not? So first we have 1's place is not on, 2's place is on, so we have 2. 2 plus, and then we say 4's place is not on, but 8 is on, so 8 we have to count in 8. And then we say 16 is on, okay, 16 is on, 32 is also on, 8, 16, 32, and also 64 is on, okay, so you have to add all these up. 2 and 8 is 10, 16, 26, 26 and 32 is what? 58, 58 and 64. Oh Jesus, did I come to the wrong gunfight here? 58 and 64. Look, I'm using a mouse. Terrible am I. Office. Oh. Do I have a calculator? Don't I have a calculator? Oh my god. I could have added it up by now. 58 and 64 is what? 132? I'm probably wrong. But I don't care. Alright? So in this area here, this byte contains the number 132 in the decimal format. Okay? That's how you would read that. Okay? Bust that apart too. Let's come up with a 32-bit wide byte. Alright? Takes 32 of these here to make up the 1 byte. Same thing over here. Bust that apart. Now you can add these numbers up and signify what they do and where they go and everything else like that. It's not important if you keep on doubling. Remember to keep on doubling. 2048. 2048 doubled is 4096. 4096 doubled. Who? Jesus. I don't know what 4096 is doubled. Alright? But you would have to keep adding. Right? Yes. Okay? That's binary. That's how binary goes across. Binary is not that hard. Just remember the rules. Alright? Remember where to read from. Okay? Read from this way in. Okay? And don't look at the numbers. Don't look at them as just numbers. Don't look at them as ones and zeros. People get confused by looking at things as just ones and zeros, as just numbers. If you signify it with something else. Say a positive and a negative volt. If you want to reverse the order, 1 is a negative volt, like Adinasoff did, and 0 is a constant positive volt. You know what I mean? Don't look at them just as numbers. They mean something. Alright? So that's that. This is how it looks in binary form on your computer. And we can say hex dump C. Let's say hex dump help. Yeah, BC. I think it's BCD. I want to say BCD. This dot show. There it is. Okay. This might be a little confusing to look at and whatever else like that, but this is all in a decimal form. Am I right? Yeah. It's all in a decimal form. Okay? Can we say binary instead? Let's take out the C and see what happens. Decimal. Okay. Let's take out the D and see what happens. Ugh, whew, man. It's kind of hard to read, isn't it? Alright? Let's put an A in. A doesn't do anything. How about O and V? OV. You know, that's the same data. It's not scrambled. It's in a different form. Okay? That's the joy that we will find out by doing more of this stuff here. By doing more in assembler, by figuring out how the computer talks, by figuring out, you know, the basics of binary, stuff like that. I would like to get into logic, but I don't know that much about logic. Alright? Maybe I will touch on some of that. And I can tell you, I can sum it up in one quick sentence and say that logic is this. It consists of 3 different gates. Okay? And, or, and not. You can create any type of logic, you can do any type of function with 3 different gates. And, the AND gate, okay? The OR gate, and the NOT gate. If you don't know what those are, I'm sorry I can't explain it right now. It's a little off topic, but Google those 3 gates. AND takes 2 parameters. It takes a 1 and a 1 to make something. Okay? That's an AND gate. Okay? AND takes a 1 and a 1 to do something. Okay? OR gate takes 1 or 0 to be on. Okay? They both cannot be on at the same time. Unlike with the AND gate, they both had to be on. The AND gate has to have one. They both had to be on for it to be on. Okay? For it to pass. If you want to call it like a... if you want to call it like... Think about it like this. Light switches on your wall. Okay? In order for you to turn on a certain light, you have to have 2 switches up at the same time. You have to have 2 switches on the wall. Okay? And you have to have them both on at the same time and your light will come on. Now with the OR gate, either one light switch can be on, okay, or one light switch on the other side can be on and it will be on. But if they are both on, If they're both on, then it is off. Okay? It only takes one or the other with an OR gate. And, or, and not. Okay? Not is if you have something on, it is reversed. Okay? When you turn the light switch on, it turns the light switch off. Okay? And when you turn the light switch off, it turns the light bulb on. Okay? That's a rough on and, or, and not gates. That's logic. It's Boolean logic. It's not complicated. Think of it as voltages. That's all. It's not complicated. Alright, gates. You can set up gates. You can set up water fountain gates, Lego gates, anything else like that. That's basically how our computers work. Gates are transistors. Alright? Well, they're not they don't only have to be transistors, but our transistors act as gates. Alright? When you power them on, they turn on. Or two of them have to be on for something to go through, for another voltage to go through. With an AND gate. With an OR gate, one of them has to be on and not the other one. If they're both on, it's not going to work. Okay? And with the NOT gate, you have one transistor that's on, but when it hits voltage with another transistor, it turns it off and releases the data, or moves the data. Alright? That's gates. And or not. Okay. I'm going to show you some assembly syntax real quick. I'm going to show you some assembly syntax real quick. Yes, I am. Where the hell did I put it? Can I say notes? Source. Source. Yes, source. Let's say CD back up. Bring a CD into source. I want to show you guys. I'm going to say Nautilus here. I'm going to show you guys some assembly, what it looks like. This is what I've said before, and as the Linux 0.01 operating system right here. First Linux ever created. Where'd I get it? I think I got it from kernel.org in the archives. You can find it, Google it, okay? And this is the boot code that Linus made so that he could boot his computer in boot Linux, and shared this so other people can improve on it and use it as an operating system, because there was you know the story, they needed a kernel, so he made it. And you see here, it's kind of historical and nice to actually look at too. He has comments in here, blah blah blah, you know, everything else like that. It's kind of, without getting romantic and sappy about it all, it's kind of freaking amazing. Alright? Now I'm going to go down to syntax. This is what assembly code looks like. Look at this. These over here are comments. We see starter hardware and all that stuff like that. This is comments, but assembly code is just this. Okay? Assembly code is move, add, compare, jump, zero, move, subtract, move, maybe repeat, I don't know, move, all that stuff, okay? Move, interrupt, call, move, XOR, alright? That's an exclusive OR, okay? Interrupt, move, jump, move, XOR, int, alright? That's the type of stuff that we're that we're going to be talking about and getting into, and I can show you some stuff. I don't know it all, but I can show you some stuff. JNC, jump not, I don't even know what that is. Subtract, okay, SHR, I don't know what that is. Increment, jump not equal, okay, jump not equal, okay. This is some of the syntax that we're looking at here. Now you tell me how you can read this right off the bat, how this is any different than any scripting language, how this is different than C. You tell me how it's different. It's Martian. Okay? It's completely Martian. If you didn't have any comments in here, you'd be totally screwed. Like over here, I have no idea what this stuff does. I don't need to. I do want to, but I don't know what it does, okay? And this is the type of stuff that we're going to be getting into. This is the stuff that really counts. It's really interesting, very low in your processor. The basic, one of like the basic forms of computing. And can you do anything with it? Like I said, you can do anything you want. It doesn't matter. But what are you going to learn from it? That's the big thing. What are you going to learn from it? You're going to be very deep inside of this thing, and you will have no limitations. I'm done talking. Have a great day. Sorry for the long video, but I got a lot to say. And I'm going to cut it off now. Alright? Have a super day.